Alright guys, so we're going to start with this exercise from Leet Code. The exercise 23 merge case order list that has a difficulty of hard. Basically, this is the exercise that is basically you're given an array of k-linked lists, which basically this variable name list is composed of all the different linked lists that are in total k, and in each linked list is sorted in a certain order. So basically, they're already sorted. And finally, it should be merged all the linked list into one certain linked list and return it. So here we have the variable like list that they have, like for example in this case k should be 3, and the output should be all the elements from the linked list in an ascending order. So here we have like first the one, then this one, and then this two, that is the first element of each element in the list, and they should be all like flattened in single linked list and return and merge in order. Also the linked list, we have like an input, an empty list, it should output an empty list as well. And if there's like an emptiness list in the input, also that should be an empty list. Constraints, so we have basically k linked list, that's already set here. K should be more than 0, it should be more than 10 to the power 4. The nodes in every linked list shouldn't be more than 500, and the elements should be in this range that are added in the nodes, and this is in ascending order basically. And the sum of the length of every node shouldn't exceed 10. The sum of this list of I and the length is basically, this should be the list of all the linked list. Basically this length shouldn't exceed this number, basically. It's correct set here. Here in this code we have these definitions where basically we have the definition for a single linked list. We have like a node that is basically a struct. It has the attribute and value of the next value. Also has here a constructor with basically has polymorphism, where basically we have one value starting with 0 and also the next value with null pointer. Also we have where the representation of the linked list when we have like a value, it's an input, and we have the next element being null pointer, and also when we have like a next value represented with a pointer, and also when the value has also like a number. These are the three cases in the constructor. So basically this is just giving us a reference, and here will be the solution that is basically designing in this class a whole method for the merge linked list, that basically we receive a vector of the linked list with basically this. In this case we will receive the node that in this case it will be the array of in a vector of the different linked lists, and we're receiving the reference of this. And basically here as we're receiving the reference to a node, basically we will be receiving basically the head node of the list. So we basically have two approaches for the solution. So basically we have the approach when it's like let's change to another marker. Okay. So we will do the approach of naive merge, where basically, for example, we will have the case when we have like, for example, this linked list, and then we have this another linked list that okay, in this case it should be in ascending order, that already in that way. So for example, this will be 2, this will be 5, this will be 7. So something that we could do is like first merge the elements from both lists and start then ordering with this. Basically this element will go further, so the final result will be something like this. This will be inefficient, as basically here we see like the size basically will be from the nodes should be n, So the complexity in memory of like every of these, basically this list should be O of n. That n represents a number of nodes, and ordering like one of this list basically will be, the complexity will be n log n. So basically this will be very expensive to do, and it will be unfeasible to do doing the naive merge. It will be one approach, but it's very inefficient in terms of memory. Something that we could also approach for the solution to be using the mean heap. Basically, this is already sorted data structure. So basically, what it will do is basically creating a binary tree representation where always these will be like in ascending order in this kind of data structure. So it will be already ordered, and we basically save from having to order the list. So for the operations that we will use in this kind of data structure, it will be push and pop. We will basically, for example, if we have like a k of 3 elements, and we have, for example, 1, 2, that will be the first list, and we have 3, then we will have 4, 5. It should be our linked list. Basically, at every iteration, we will have one reference to one node of each list. So the complexity of this operation will be O of k. The complexity of every of these operations will be log of k, then giving a complexity, a final complexity of basically of n log of k. Then let me write it down here. So basically, with the mean heap, basically we will have a final complexity of n log k, being more efficient in avoiding to then having to first merge and then having to also sort the list. So that's the approach that we're gonna use. So basically, the mean heap by default is in a descending order. So basically, in order to use this, we should do a priority queue. Where it will basically first have the type of element that we will have like in our vector that is by default in the priority queue, and then we will specify the vector that we will have, that it will be basically a vector of this node, that will be basically a vector of nodes, and then we will have the operator in order to sort basically the elements, or define the way that the elements are basically sorted in the list. For which case we're gonna create lambda function here in C++ in order to modify the default behavior that will be descending order in the priority queue to an ascending order. So basically here we're gonna do an empty list here to indicate that there are no variables inside the scope that we'll be using as basically it will be necessary to use any variable in this scope. Only basically it will be a captureless lambda function, as it will only capture the elements in the parameters of this lambda function. So the first variable type would be of node list a pointer, and would be another node. So basically we're going to be comparing nodes from the list in every case. So basically comparing two nodes from the list, we're going to return, and you're going to access from the basically from this node the attribute of the value, indicating basically if the value from the first node is greater than the value from this node, it will return true or false accordingly. So basically, if this returns true, means like this value will be greater than the value that is in B, in which case we're gonna do basically an order that is gonna be ascending in this list. We're gonna basically go from the smaller to the greater. Finally, here, as this is a lambda function, it doesn't have like a name during compilation. We're gonna here indicate that the way that we're gonna order the elements in the list is gonna be from declaration type, and is gonna be the lambda function compare. We're gonna then indicate the min heap with operator the lambda function compare. So basically here we have the priority queue, that is the data structure that we are going to use in order to be populating the elements that we're gonna be extracting from every node. So basically this is gonna be in ascending order. We're gonna start with the lower elements going to the greater elements. So here we will start having the first node that should be the smaller values, and we're gonna start populating the priority queue with those values doing the pop operation. But basically here we will have a for loop that should be every node from this variable, this iterator in the for loop, coming from the array of lists. So basically here, if the lists are not valued, are not like empty, then we're gonna do the push operation of every node in the heap. So here we're gonna do the push operation in the heap. This implies that first we're gonna have, for example, in this example, we're gonna have the 1, 1, and 2 inserted in the min heap, and from there we are gonna start merging the already ordered elements in the final linked list that we're gonna return. In order to return the final merged list, basically here we're gonna create a dummy list when we're gonna basically initialize this in dynamic memory with the dummy value of -1, and I'm gonna start y in this way in a second. We're gonna also need another auxiliary variable named current that is gonna be basically same as the address of dummy. So basically here we're gonna initialize this dummy list that is going to have the same address in memory than this current variable, basically. So what we are doing here is that we first have, for example, in the heap, we're going to have the elements that are going to be 1, for example, 1 and 2 that are coming from this input. As we're going to have this initially, we're going to be inserting in the final list, and we are going to initialize the list in -1. So basically, when we create the final result, simplifies handling the head of the first result, basically. So what we're gonna do is that we're gonna insert first element, where we're gonna like avoid handling, for example, the next element that would be, for example, in the first list, if we have, for example, 1, and the next element will be null, for example, we are like avoiding, like basically dealing with the head of the first result in each case. For example, we have like these different lists, that this would be the final merge of the min heap, for example. But let's suppose that these are two separate lists. Basically, if we merge them, doing like in the example, when these, for example, we will have this. This will finalize in null as well. So basically what we will have is we inserted the dummy node here in the beginning with -1. So what we're gonna do is we're gonna insert this node indicating like we are not gonna like handle the what is the head of between these two lists, for example, or k list, but we're gonna just start in 1 and we're gonna start merging the nodes in the final result, and we're gonna return from this onwards. Basically, that's what we will be doing. So once these are initialized, let's consider that this is like the address of the element of this element which has like created this node, basically. So as we are assigning the dummy variable to this current in this auxiliary array, so basically they will both have the same address, and we're going to modify this current array. So we are basically modifying dummy in the same address that has already this dummy node. Then we already inserted the first element of each list, the node, into the min heap. Now we're going to start traversing the whole heap. So we're going to do a condition for this structure while it's not empty. Then we're going to return, or we're going to get the smallest value, creating a variable from this node that is going to be smallest, and we're going to get this element from the min heap of these three of these elements, let's say 3 in the example, using top. So we get the smallest value, this is in an ascending order. Once we get the smallest value, you're gonna basically do the pop operation to take this value out from the structure. Once we got this value, we're gonna insert the smallest value into the current auxiliary list using the next element. We're going to assign that the next element is going to be the smallest, and then we're going to modify the whole node, adding the next value. So now, for example, we started with the auxiliary node, the domino that was -1. So we will have -1, and as the next value is the smallest in this case could be 1. So now we have 1, -1, and then we have like 1 inserted. So we already insert the smallest value, and we're gonna iterate for all the list, basically adding every value that is the smallest in each node. Now, to keep inserting nodes in the heap, we're basically gonna check for the smallest node. We're gonna check for the next if it's not null. If it's not null, then we're gonna basically do the push operation to basically insert the next value in the heap. So basically, for example, we inserted 3 nodes in the beginning. Let's say, see in the input example here. Here, for each of the lists, basically, we inserted the first element, the 1, and the 2 here. Then, basically, we get the smallest value from the list. We add it to this current list here. So now the final list will be having every element at a time. From this smallest value, it will have a next element. In this case, for example, it will be the next element will be 1, for example, because we already popped this 1. So as this as the next element from so from this smallest value, for example, in this case it will be 1 or this 1. In this case, in this specific example, it will be this element. So for the element that we popped, it will have the next element that will be a 4. So this 4 will be pushed in this structure, in this main heap. Then it will happen, for example, the next case, the smallest will be this 1. So the next element of this will be the 3. In the next case, it will be 2. That is the smallest, and the next will be 6. As, for example, in this case, the next element of 6 will be null. It will insert more, and it should just leave the conditional statement. And this is what concludes the cases for basically extracting the values from the linked list. Once we have basically all the values like push and pop from the main heap, we will have a final result that we will create in this variable. Basically, that will be the dummy variable starting from the next. Why the next? Because we are already inserted this dummy value here, so we'll start from the next. And the advantage here is like here we are gonna free the dynamic memory that we basically allocated here, and as this list node basically already contains the variable, we're just gonna return the result. The advantage of assigning this variable result for the next element is like now we can free the memory allocated from this structure and just finally get the result. So here are basically including the exercise. We're just gonna submit the exercise. Here is an error, as this should be val. This should be val, not value. There's a typo here in the name of the variable. Here there should be a semicolon that is already here. This one. Okay. You have like a missing semicolon here for this lambda function. Oh, okay. And here we were using the specific list in the loop, basically, not the whole array, but every element at the time, every node. And here it's a typo. Same as here. And here as well. So here we have the solution. It's already accepted the solution. We're gonna analyze the time complexity. As we can see, using this solution with the heap is the final complexity should be O and logarithm of k. Thank you so much.